Okay. So how to find conserved motifs. So we've already done multiple sequence alignments. That's one way to find conserved motifs between your different sequences. But there's also cases where sequences can have motifs in common, but the sequences themselves are not actually related. So let's say, you have like an import, a protein localization signal, or you have a promoter sequences that are otherwise unrelated, but they all have binding sites for transcription factors. And then you have to use a different kind of method to find those. Then you can't use multiple sequence alignments. And again, here we come to sequence logos, which is a great tool for this. Yeah, this is what I said in the last presentation. Basically, the relative size of each residue reflects the frequency of that residue within the motif. And also it tells you, so in this case, it tells you that A is the most common, but there's also many cases where the third position has something else. So it's not that highly conserved. A is the most common, but it's not that conserved. But then the fourth position basically always has a G. That's how you interpret the sequence logo. And when you do this kind of analysis, you have to make sure that your sequences are functionally linked. So that can either mean that they are homologous to each other, which is, if you're looking at protein sequences, or that they have a conserved function, or they're regulated the same way. So if you look at promoter sequences, you would look at genes, like sequences that are all part of the same pathway. If you look at promoters of genes that appear to be regulated the same way. So if you have transcriptome or proteome data and you notice that genes behave in the same way, you can analyze their promoter sequences this way. Or if you're looking at protein sequences, let's say protein sequences that all go to the same organelle but are otherwise unrelated, well, then it might be worth to do a motif search of that to see if you can find a motif. So when it comes to promoter sequences, it's a lot of work. The simplest way to do it, if you have genes in the gene database of NCBI, you can just go in. You remember there was the sequence viewer window, and you can see your gene, and then you can just basically copy paste the sequence between your gene and the gene up ahead, the one that's upstream. You can also go into the genomic DNA sequence record and basically look at the genomic coordinates for your gene and then the gene that is upstream, and then basically go to say which part of the DNA sequence you like. The most annoying way, if you don't have annotation information and you've located your gene in a genomic sequence, you basically take a chunk of the upstream DNA and just do a BLASTX search to see if there's a protein somewhere there. And then using that protein sequence, you can determine where that begins and where your sequence begins, and then you can extract the DNA sequence in between. So when you do motif searches, you should try and have as many sequences as possible. It would be ideal if they are as short as possible, but that's beyond your control. I mean, it's just nicer if they are short, because then that information has a smaller place to hide. When you have promoter sequences, basically the orientation of the upstream gene can make it more or less difficult for you to find motifs. So what you like is what's called a tandem orientation, and I'm going to show you that in the next slide, where basically the two genes point in the same direction, which means that any motifs in the promoter region is only going to apply to your sequence. But then you have this thing where it's divergent orientation. So your gene points in one way, and then it's sharing a promoter with another gene, which means that the promoter sequence will contain regulatory information for both genes. And that can lead to basically contamination of your sequences with other regulatory elements that has nothing to do with your gene. It has to do with the other gene. And then, of course, you have to be careful. You have to be as sure as possible that your input sequences do actually have a functional relationship, because every time you put in a sequence that has nothing to do with it, you're diluting.
Or can you just see him?
Just see him.
Did someone have a question? Okay. So if you put in like an unrelated sequence, a sequence that has nothing to do with it, you're basically, you're diluting the information. So it's basically adds random noise. So this is basically this. If this is your gene of interest, this is its promoter region. This is the ideal thing, because the upstream gene, its promoter will be here. So the only motifs you're likely to find will regulate your gene. But if you have a divergent orientation, then the upstream gene will also have regulatory motifs in the promoter sequence. And so then you run the risk of picking up basically the motifs of the other gene that actually have nothing to do with the regulation of your gene that's over here. When you look through your data sets, so again, now we're talking promoter sequences, you should try and avoid sequences that are longer than 3 to 5 kb, because they just dilute your data sets. So just try and throw those out. If you have very long promoter sequences, check them for undetected genes with using BLASTX. I would also avoid having several input sequences that are really similar to each other. So if you have, for instance, from closely related species, their promoter sequences can be quite similar. And that then you have a risk of picking up false positives, because the thing is, as species diverge, most of the sequences will also diverge except those motifs, and that's what you're hoping to pick up. Also be careful when you have when you have a promoter sequence and you're not sure where the upstream gene begins or ends. So you're not sure exactly where to draw the line of where is the promoter sequence. Like, you know where it starts from your gene, and then the other one, where does it begin or end? And then you might want to think of like not including those sequences. You should also throw away any DNA sequences that has ambiguous nucleotide bases. That's worth checking. It still happens that you will have genome sequences where there's just a bunch of N's because they don't know what it is. And also, if you have a pseudogene, that can also mess up your data. So keep an eye out for that. One thing I always do is just check if there is any tRNA sequences in any intragenic regions between two genes, because that can mess up your data as well, because they're so small that they can fit there. And then you also run the risk of picking up regulatory motifs for tRNA transcription. So there's quite a good database server for scanning for tRNA genes. So the algorithm we use for checking for these motifs is called MEME. And it's basically, it just looks for motifs that are statistically overrepresented in sequences. And it works both for DNA and protein. And then, but the thing is, you have to tell it, the algorithm can't figure out what is significant. You have to set the parameters to guide it. I'm not sure if this is true anymore. It might even have increased, but there is a you can do quite significant searches now. And then just like with BLAST searches, MEME will give e-values. And then again, what you're striving for, just like with homology searches, is a low e-value. And this is what the input looks like. I'm going to show you this. I'm going to demonstrate it to you. So you can either copy paste or upload a file, depends on how many you have. Then you need to tell it what you basically have to say what do you expect? What kind of frequency do you expect to see? So it goes either 0 or 1 per sequence. It goes 1 per sequence or any number of repetitions, if I remember correctly. Then you tell the program how many motifs should it dig up. And it will just basically stop after it's found that number. So I normally go 10 to 20. And it will just keep going. Even if it finds bad ones, it'll just keep going for as many as you've asked for. And then down here, you can put like how wide do you expect the motif to be, and what is the expected frequency in each of your input sequences. What is the kind of the range of the frequency that your motif will have. And the lower you set, it's going to be really strict, and the higher you go, it's going to be less strict. And then you also have the possibility of searching for palindromic sequences in DNA. And what I do is with promoter sequences, I do both. Yeah, so this is basically, I always recommend that you start with any number of repetitions. And then, as you saw here, you can, once you've said that, any number of repetitions, you then set what you think the frequency will be. And I normally, what I do is it's actually what it does is it doesn't say per sequence, it kind of says for all the sequences. So you can have some sequences where there will be none, and there will be some where there will be many. But it will basically calculate. I mean, you will notice this when you do the search. It will look for like the total number of motifs in all your input sequences put together. And the simple rule of thumb I have is that if I have a number of input sequences, like number of promoter sequences of n, I always start the range with half of that number to double that number. So if I have 20 sequences, I will go between 10 and 40. And I always start for DNA sequences. I always start with 5 to 22 bases in the motif size. And then you can just see what the result looks like, and you can just tweak it to see if you can improve it. And many DNA binding sites, if you're looking for transcription factor sites, many of them are palindromic. I always do both though, to see. And in some cases, this is something that's happened to me, is that you will have a palindromic site, but then you will have a site right next to it that's non-palindromic. So this is kind of tricky, because you will, if you do the palindromic search, you will pick this up. But then if you do the non-palindromic, you will start to see that on one side of the palindrome, there will be something else that's non-palindromic. And that's why it's worth doing both. So yeah, so here you can see, this is my data, where basically there is one palindromic site here, and then there's a non-palindromic site right next to it that's bound by another transcription factor. And these are related genes. And if I just do palindromic, I will only pick up the palindromic site. But if I do non-palindromic, I will also pick up the site that's right next to it. So again, always good to do both. This is what the result page will look like. And again, I always just go for the first one. And this is what your output will look like. And again, we will run this. So you will have your significant hits. The cutoff is 1 in 100. So 1e minus 0.02. No, sorry, minus 0.002. That will be the cutoff. And then you see the ones that are not significant are kind of blurred here. And then you can go into your motifs. You will see exactly where in your sequence the motif is located. And then you can go in and actually download it. So you can download it if you just want it for a presentation. You can download it as a PNG, but there's also others. I think it's EPS. And you can also go from the there's the forward and reverse. So now it's showing on one strand, but if you want the opposite strand, you go I think it's the orientation one, and you can change and get the other strand. And then, you know, as sample size goes up, so now I have, this is the data set I've given you. If you go up to 52 sequences, you can see you can get this really nice expect values. Here you can see another interesting thing. So this probably, I haven't explored this. I don't actually know what the transcription factor is, but if you look at how this motif looks like, right? You have these double C, double G that are the highest conserved, and then you have the spacer. Then on either side, you have these sequences that seem to be less conserved, but still conserved. But notice what happens if you do the palindrome, right? The program is going to try really hard to make a palindrome, and that's what it's done here. But if you tell it to do non-palindromic, then what the program does is it pushes all the sequences to, because it doesn't care which strand it is, so they can flip them around. So what it does to maximize the score, it has actually moved all of these to one side of the motif just to get a higher score. So that's why, and you know, this might be a directional site, I'm not sure. Oops. But that's why it's always good to do both palindromic and non-palindromic. The last thing I wanted to show you is that you can use motifs to get an idea of function, which is kind of part of this course, is that you can, so in this case, again, this is from one of my papers, where I looked at a group of genes, and then I analyzed their promoter sequences, and I kept getting this one motif. And I happen to know that this motif has to do with sulfur assimilation in yeast, and therefore I could draw a conclusion saying these genes are probably involved in sulfur assimilation, just as a demonstration. Right, so I just want to show you now how to do this. Right, there's right. So here, this is the thing I sent you. These are sample promoter motifs. Just going to collect them all. And now say meme motif. Because if I search for meme, I'm going to get half the internet. There we go. I want motif discovery. There we go. Right. Type in sequences. There we go. I want any number. Give me 20. And we call this course. Right, I have 52 input sequences. So 52, that's half of 52 is 26, and double of 52 is 104. And again, what did I say? I said 5 to 22. And yeah, let's say look for palindromes only. Okay. Where's the button? Am I blind? There it is. Start search. There we go. And now that's going to take a while. Okay, so that's how you do it. Now, Beatrice, you can stop recording.